Hello, my name is Alexis Cordova and welcome to my Spring 2015 Chemistry Honors video. Today I will be teaching you how to solve the following problem, which states, imagine that you have a chamber in which a chemical reaction is taking place. The chamber is surrounded by 1,000 milliliters of liquid water at room temperature. If approximately 250 moles of a product is produced in the reaction, what change will be experienced by the water surrounding the reaction chamber? In order to solve this problem, we must take multiple steps. The chemical equation of the chemical reaction that we will be using throughout the entire video is ammonia and oxygen gas react to form nitrogen gas and water. There are 3 elements involved in this chemical reaction, including nitrogen, oxygen, and hydrogen. Included in this table is information on each element, including the electron configuration. Next, we will find out how to find the electron configuration of a neutral atom of an element. In order to find the electron configuration, you must know that there are a total of 7 energy levels, and each energy level contains sublevels that are S, P, D, and F. Each sublevel contains orbitals, which are regions of space where the electrons are likely to be found. An orbital can hold a maximum of 2 electrons. Here's a table showing the sublevel types, their amount of orbitals, and the maximum number of electrons they can hold in total. Electrons fill orbitals in a way to minimize the energy of the atom. We are now going to find the electron configuration of a neutral atom of nitrogen. We are going to be using the diagram to the left, which can help us determine in what order the sublevels will be occupied by electrons by following the arrows. Firstly, we must identify the atomic number of nitrogen, which is 7, because in a neutral atom, this is the number of the electrons. We will start with 1p, but since it can only hold 2 electrons, we will write 1p to the power of 2. We must then continue because there are more than 2 electrons. Next, we will continue with the next sublevel, which is 2s, and since we know that it can only hold 2 electrons, we will write 2s to the power of 2. Next, we will continue with 2p. Looking at the chart, we can see that the p sublevel has 3 orbitals. Therefore, it can hold 6 electrons. Our neutral atom only needs 3 more electrons to reach 7, so we will simply write 2p to the power of 3. We are then left with our final electron configuration for a neutral atom of nitrogen, which is 1s to the power of 2, 2s to the power of 2, and 2p to the power of 3. We know that our chemical equation is unbalanced because if you compare the atom counts on both sides of the equation for each element, they are not equal. Therefore, this equation is unbalanced and it does not agree with the law of conservation of mass, which states that matter cannot be created or destroyed. So because it's unbalanced, we can now balance it. In order to balance this equation, you must take the following steps. Firstly, we must divide the equation down the arrow with a line. Secondly, we must list the elements on each side of the equation using the same order as the previous problem. Thirdly, we must count all the atoms of each element on the reactant side of the equation. Fourthly, we must count all the atoms of each element on the product side of the equation. Fifthly, you must add coefficients to a reactant or product to try and balance one element. Sixthly, you must update your count of atoms on that side of the equation. Lastly, you must repeat steps number 5 and 6 until the numbers of atoms on each side of the equation are equal. Now our equation is balanced because the number of atoms for each element in the reaction are the same for both the reactants and the products. We will now use this balanced equation to find the enthalpy of our reaction. We must start out with knowing the enthalpies for each reactant and product in our equation. We can find the enthalpies using a table of enthalpies of formation. This chart states all the enthalpies that are needed for our equation. Nitrogen gas is equal to 0 kilojoules per mole. Water in the liquid state is equal to negative 285.8 kilojoules per mole. Oxygen gas is equal to 0 kilojoules per mole. And lastly, ammonia is equal to negative 45.9 kilojoules per mole. We must then multiply each enthalpy by the coefficient that is in front of it. For example, water has a coefficient of 6, so we must multiply 6 by negative 285.8, giving us negative 1,714.8. Once we do this for all the reactants and products, we must then add the reactants together and then separately add the products together. Then we can plug these 2 numbers into our equation. The equation is located at the top of the slide, in which we must subtract the enthalpy of reactants from the enthalpy of the products to give us the enthalpy of our final reaction. So we set it up as negative 1,714.8 kilojoules per mole subtracted by negative 183.6 kilojoules per mole, which will end up giving us negative 1,531.2 kilojoules per mole, Because the final number is negative, we can conclude that this reaction is exothermic. It is releasing heat to its surroundings, and in addition, the enthalpy of the products we calculated is lower than the enthalpy of the reactants. Next, we will find the amount of energy that is released by our total reaction if approximately 250 moles of product is created. We can do this by simply multiplying the enthalpy of our reaction by 250, and we will end up with negative 382,800 kilojoules per mole. Before we move on to solving the last step of the problem that was introduced at the beginning of the video, we must now change the number that we just calculated from a negative to a positive. We must do this because in the next problem we are simply focusing on the water, and our reaction is giving off energy that the water will then absorb, and this will increase the temperature of the water. This is why the number must be changed to a positive. We are now going to be solving that problem that was introduced at the beginning of the video. We're going to be finding the change of temperature of 1,000 grams of water that is at 21 degrees Celsius. We are firstly going to identify the components we will need for this equation. Because we know the equation is Q equals M times C times delta T, we know that we must figure out what the mass is, what the change in temperature is, and what the specific heat capacity for the water is going to be in order to solve this. We know that our mass is equal to 1,000 milliliters, which is equal to 1,000 grams. We still must find the change in temperature, and we know that our specific heat capacity is 0.00418 kilojoules. I was able to find this because I know that 1 joule is equal to 0.001 kilojoules. We are finally going to be solving for the change of the temperature that is unknown for now. We are going to plug the known values into our equation, which is Q equals M times C times delta T. Because we are solving this based on the amount of energy released by our reaction, we can substitute 382,800 kilojoules per mole as our Q. Once we plug all of our numbers that we know into the equation, we can multiply 0.00418 kilojoules per grams degrees Celsius by 1,000 grams, and we get 4.18 kilojoules. Since we are trying to solve for the change in temperature, we must isolate delta T by dividing both sides by 4.18 kilojoules in order to get delta T by itself. We must then divide 382,800 kilojoules by 4.18 kilojoules to get 91,578.95 degrees Celsius. This number is our change of temperature. Now that we have found the change in the temperature, we are going to be finding the final temperature of the water, which can be found using the equation that the change of temperature plus the initial temperature is equal to the final temperature. So we can plug in the numbers that we do know, which we do know that the change in temperature was 91,578.95 degrees Celsius, and we know that the initial temperature was 21 degrees Celsius. So if we add these two numbers together, we should get the final temperature, which would be 91,599.95 degrees Celsius. I was able to use this final temperature to help me predict what phase change I think the water in this problem will undergo. So I predicted that the water in this problem will undergo the boiling phase change because it started off as a liquid and ended up as a gas. We know that it started off as a liquid because the water was at 20 degrees Celsius, which is between 0 and 100 degrees Celsius. And we know that it ended up being a gas because our final number, which is 91,599.95 degrees Celsius, is greater than 100 degrees Celsius, making it a gas. We have now finished solving the problem that was introduced at the beginning of the video, concluding my Chemistry Honors 2015 video. Thank you for watching.